Okay, so now we are talking about free fall, okay, objects that fall. And the idea is the following. When we have free fall, we have a uniformly accelerated motion. Okay? Uniformly accelerated motion. There is a motion where the acceleration is constant. So those equations that we derived before will apply here. And Galileo Galilei was one of an important person behind these studies. What he realized was that the objects increase their speed as they fall, and the distance that these objects increase, the distance that these objects travel, is proportional to the time square. Okay? And he did experiments to support that. He went up in the Pisa Tower and threw objects from different heights, and he concluded that it would take time t squared for the object to fall that specific height. And so he went different heights, repeat this experiment many times, and he was able to find this correlation, to find this expression. Very well. One important aspect of this research was to be able to simplify, to idealize the motion. What is the idea? Well, usually, if I ask you, if I have a piece of paper, okay, and another object like a pen, and I ask you, if I drop both from the same height, which one will reach the floor first? And people usually tend to say that it is the pen, and they tend to say that the pen is heavier. Okay, if we do the experiment, and this I suggest, I advise you to try, you really do see the pen reaching the floor first. But let's think a little bit. Why is it reaching the floor first? Does it have anything to do with its mass or not? Well, if you repeat the same experiment, but with this piece of paper, okay, with this wetted up piece of paper, it's the same piece of paper. But if you repeat the experiment, you will see both reaching the floor approximately at the same time. So what is changed? This piece of paper is still the same, but here it was open, flat, and the second case it was all wetted up. What is the difference here? Well, when we have a piece of paper like this, and we know that here we have air, all these molecules of air are colliding against our big piece of paper, this large surface, and they are holding this object as it falls. Once we wet it up, the resistance is not the same anymore. And then the resistance of my pen and the resistance of this piece of paper start becoming very similar. Once we think like this, then we can say, well, if I was able to remove all the air from this room, then for sure both will reach the floor exactly at the same time. So what was responsible for the difference in time for these two objects was not their mass. Mass is not important in the free fall. What was holding the piece of paper was the resistance. I remove the resistance, I remove the molecules, and they fall together. So from that we conclude that the free fall does not depend on the mass of the objects, it depends only on the acceleration. And which acceleration is that? This is gravity. Okay? This acceleration is the acceleration caused by Earth. Earth is this big planet that attracts all the objects around it. Okay? And so this is Galileo, right, who is the father of modern science, and he was able to do this idealization, this simplification, to try to tell us what we would expect. So in the absence of air, in the absence of any resistance, all the objects will fall with the same constant acceleration, and they will all get to the floor at the same time if we release them from exactly the same height. And what is this constant acceleration? gravity, what is the value? 9.8 meters per second squared when we are very close to the surface of Earth. If we start getting too far from Earth, then there are deviations, this magnitude decreases, but for this point, for all of these problems that we'll be solving at this moment, g is just 9.8. Okay. Acceleration, as we said before, is a vector. So this is the magnitude of this acceleration, and what is the direction? The direction is always toward the center of Earth. Earth is attracting everything. And so the direction is always down, okay? Always towards the center of Earth. Once we agree with that, we can say that if, this idealized world where resistance, air resistance does not exist, all of those equations, all of those 4 equations that we talked about before, apply again. And what I can do, if you want, but this is not necessary, since before we will talk about horizontal motion we were using x, well, now you can use y. Not necessary, but this vertical motion, then we use the equation for position in y, the equation for velocity, the equation for velocity with displacement when we do not have time, and that average velocity. Okay, this is an important point now. We'll have to choose a reference frame, and it's totally arbitrary. I can call up being plus, or I can call down being plus. It will depend on the problem that we are trying to solve. We can try to make it this choice of the reference frame can make things a little simpler, that's all. But the choice of reference frame should never affect the results. The results will not be affected by that. They will be exactly the same. Can just be, there can be more convenient frames. Okay, so let's try to start solving some problems. And then at this point, since many students still do not have a calculator, what I did is I used g equals 10, an approximation for the actual value, which is 9.8. I'm going to be using g equals 10 at this point, just to get simple numbers, okay? But as soon as we finish this problem, we'll move on and put the real value 9.8, okay? All right, so let's start with the same problem, the first problem. A ball is dropped from a tower 70 meters high. When we are solving these problems, make drawings. Drawings are very helpful, okay? So the ball is 70 meters high, so it's dropped. So I'll put here 70 meters high. If it is dropped, we know that this initial velocity is 0. This is important information. And we want to know how far will the ball have fallen after 1 second, and then after 2 seconds, and then finally what will be the magnitude of its velocity at this point. Okay, as we said, acceleration, when we are in free fall, the acceleration is always pointing down, and in this case we are saying that it's approximately 10 meters per second squared. We have to choose a reference frame. The reference frame, as we said, is totally arbitrary. It's sometimes, or usually it is convenient to choose our initial position where the motion starts. That's what I'm going to be doing here. So right where the motion starts here, I'll be saying that this is the initial position, that is for sure, but I'll associate with this the origin of my reference frame. And I'm going to say that down is positive. That's a choice. You could have said that up is positive, okay? I'm just making a choice. Once I made this choice, then only after I made this choice, I can then associate a sign with the G. I see G and my frame having the same direction, then I can say the G is plus. Okay? Alright, with all that, I now move to the equations. I want to know how far will the ball have fallen after 1 second. Okay, I'm going to use that equation for position. I want to know what is the displacement, right? Because how far will the ball have fallen? So what I really want to know is y minus y naught. Okay, so this is displacement. And this is V naught t, but V naught is 0. I don't need to write anything. G is 10, right? And 10 divided by 2 is 5 t squared. So this is the equation that I have. Then here I just need to put 1 second and I'll get the displacement. And the displacement, this how much we travel, is 5 meters. For 2 seconds, well, 2 seconds squared is 4. 4 multiplied by 5 will give us 20. Okay. Now let's do the same thing for the velocity. Well, let me write the equation for the velocity. V is equal to V naught plus just gt, right? And I will rewrite this equation as V, since V naught is 0, I'll just write V is equal to gt, right? So, again, G is 10 plus 10, time in 1 second will give us the velocity 10 meters per second. At time 2 seconds will give us 20 meters per second. Okay, and they just asked the magnitude, so I just need to give the number. But if they were asking us really the velocity, then I would have to put the magnitude and also the direction. One way to write the direction is just to say pointing down. That's a direction. And pointing down in my case is plus, so you could say plus. But you have to show the reference frame so people understand what this plus means. Or you just say down, pointing down. Pointing down is enough. Okay. Now consider the same exercise, but suppose the ball is thrown downward with a speed, with an initial velocity of 3 meters per second. Okay, so now things are changing. My velocity is not 0, my initial velocity is not 0 anymore, but now it is plus 3 meters per second. And plus because it's pointing down, and it's going together with my reference frame. Okay, so what will change here? Well, the V naught is not 0 anymore, so we'll keep this V naught here. And so in this equation here, I will keep my V naught, 3t, and G, we assumed was 10, so 10 divided by 2 is 5, t squared. So this is the equation that we need to find the how much we travel after 1 second and how much after 2 seconds, right? So after 1 second we have 5 plus 3 is 8. After 2 seconds we have 5 multiplied by 4 is 20, 3 multiplied by 2 is 6, so 20 with 6, 26. Same thing now here. This equation, we'll have to take into account the V naught. So the final velocity will be plus 3 meters per second plus 10 multiplied by time. When time is 1, we get 13 meters per second. When time is 2, we get 20 plus 3, 23 meters per second. Very well. If you change and do a different reference frame, you will see that you will be obtaining the same results. Okay, the change in how far we travel will result in the same values. The magnitude of the velocities will be the same. The sign may change, right? So let me just give you an example here. Suppose we choose a different reference frame. Okay, so my reference frame now is pointing up like that. I have to choose an origin again. Suppose you like to choose your origin, the floor. Okay, so this point here will be 0. What would we say about our initial position? So I'm solving now this problem 2, okay? This problem 2, but with this reference frame. So if I call this my 0 position and my frame is going up like that, so my initial position now will be what? This height is 70, So my initial position will be plus 70 meters. Okay. How about my initial velocity? Well, my initial velocity, we are throwing it down, right? We're throwing it down. So my initial velocity is opposite to my frame. So my initial velocity is minus 3 meters per second. So we have to be very careful with that. Same thing about the acceleration. The acceleration is always pointing down. And my frame, I chose it up. That means my acceleration is opposite to my frame. So my acceleration now is minus 10 meters per second squared. Okay? So we just have to be careful with these signs because of this choice of reference frame, but everything at the end will work similarly. Let's try to get one case, how much the object traveled after 1 second. Okay, so here we have our equation for position. Y is y naught plus v naught t plus g over 2t squared. So we are interested in how much we traveled, so we're interested in y minus y naught. Alright? And what do we put for the velocity? Well, now we have to put minus 3t. What do we put for the g? Minus 10 divided by 2, so minus 5t squared. See? So this is our equation now. Once I put 1 second, I'll get 3 and 5, so I'll get minus 8 meters. So the magnitude is still the same. How much did I travel? 8. My displacement was negative because it's opposite to my choice of reference frame. Okay, but the problem was not so interested in knowing directions. No, it was interested in knowing how much I travel, what is the magnitude of the velocity. So the sign was not even that important. Okay, all right. So now let's go for another problem, which is problem 3. So in problem 3, what do we have? A person throws a ball upward. So now we are here on the floor. The person throws a ball upward, and this initial velocity is 20 meters per second. You see that I left some space here because I haven't chosen a reference frame yet, so I don't know if I should put plus or minus there. Okay. First question is how high it goes. Okay, how high it goes is related to distance with displacement, and that's it. Doesn't give us any other information. What we know for sure? Well, we know for sure that we have g, and that g points down. We are assuming g being 10 meters per second squared, whereas 9.8, we're just approximating it in this case. Let's make a choice of reference frame. Let's make a choice of reference frame, so now I can put the signs for V naught and the sign for G. I'm going to choose my reference frame pointing up. Okay, it's an arbitrary choice, and once I make this choice, I know that my initial position is 0, because I'm calling this the origin. I know that my velocity is pointing up. My frame is also pointing up, so my velocity is plus. I know that G is pointing down, opposite to the frame, so it's negative. That is good. Now we can go and try to solve the problem. Okay, so first thing is always to choose a reference frame. Okay, how high it goes. Okay, I could think of 3 equations. Let's see what would be useful for us. That equation for position, would it be good for us? Let's have a look at it. Well, the problem with this equation is that it requires time, and we do not have time. Then we will need to go to another equation, get time, and then substitute there. Okay, so this equation by itself is not enough. The equation for V, if I go for the equation for V, which is V equals to V naught plus GT, would that be good? Well, for sure that equation will not be giving us how much we traveled, but that equation can give us time. So this is a good equation if I use it combined with the equation for the position. Okay, if I combine those two equations, I can get the time from this one and then go into the other one. Yeah? Let me write the two. These two combined can be useful because from here I can get the time. Once I put the time here, I will know how much we travel. Okay? Okay. Let me start with this one, but there is an easier case. But let me start with this one. So how would we combine these two? How can I get information about the time from this? At the highest point, what happens to the velocity? At the highest point, the velocity will go to 0. It goes to 0 because the highest point is when the object stops to then fall down, back. So the highest point of the velocity is 0. From this equation I could get the time. Once I have the time I put it here and then I would get how high we went. Okay, this is one way. The other way is to go to that other equation where we do not have any time. So then I can solve the problem just one equation. And that equation is v naught squared equals to, v squared equals to v naught squared plus 2 g delta y. Okay. We already discussed what is the velocity at the highest point. The velocity at the highest point is 0. That's when we stop. What is the velocity at the initial point? Well, that is not 0 because otherwise we will never go up. So in this case here is 20. 20 squared is 400. Okay. What is g? Well, negative. Careful with that. So here we get minus 20 delta y. And then from here you will finally get that how far did we travel? 20 meters. Okay. Okay, how long it takes to reach that maximum height? Well, now that I know what is this maximum height is, I can go either for the equation that involves position. This equation, now I have the delta y from here, I will get the time, or I can go for the equation with velocity. Which one would you pick? Well, look, there is a big advantage in using this one here. Now we just want information about time. And what is the big advantage? This is a linear equation, so I don't need to solve a quadratic equation. Both will work, okay? But I'll pick the easiest one, okay? And how then we solve? Final velocity is 0, initial is plus 20, g is minus 10 divided by 2 is minus 5, and from here we are going to get the time, right? Oh, there is a mistake here. This equation is v naught g multiplied by time. Oh, okay, so this is this equation. Now I know the final velocity is 0, the initial is plus 20, g is minus 10 with the time, and we get the time 2 seconds. Okay, so how long does it take to reach this highest point? Well, it takes 2 seconds. And what is this highest point? Well, plus 20 meters. Okay, and this is 20 seconds. All right, now, how long the ball is in the air before it comes back to its hand? So how long it's all in this whole trip, going up and then coming back. Okay, goes up and then comes back. How long does it take? Well, you don't need to do any calculation for that. It takes 2 seconds to go up. It will take 2 seconds more to come down. So the time, so that question C, you can just go straight and say 4 seconds. Okay, so for B, we got the time was 2 seconds. So we know for sure that C is 4 seconds. If you don't believe, you want to go and double check, go on. How would you do that? Well, you could, for example, use this equation here. And how would you use this equation? Well, the final position, when we are back here, is 0. What is the initial? Well, the initial is also 0. What is the initial velocity? The initial velocity is plus 20. with t. And what is the g? G is minus 10 divided by 2, minus 5. If you solve this equation, you will see that you get those 4 seconds. Okay? So it's always good to be skeptical, as we said. This is the spirit of a good scientist. No? So go on and check. All right. The other question is, what is the velocity of the ball when it returns to the person's hand? Well, again, this is one that you don't need to do any calculation. The velocity, well, it left with plus 20. It goes all the way up, stops, and then comes down. So the same motion that it did up, it's going to be doing down. It's just a change in direction, but it's the same motion kind of idea. So if it started with plus 20 meters per second, when it gets down, it will be again with 20 meters per second, but pointing down. So the only thing that changes is this sign. Again, you don't believe me, you don't trust, well, go for the equations. You just found that the whole motion takes 4 seconds, all right. So you can use, for example, this equation, v equals to v naught plus g. Again, I'm obsessed with that g over 2. So v equals to v naught plus gt. You know that the whole motion takes 4 seconds. And then, okay, let's write the equation. You want to find the final v. The initial is plus 20. G is minus 10. Minus 10 multiplied by the whole time, 4 gives us minus 40. And you see, you'll get minus 20. Okay? All right, let's go for the last question. So the last question is, what is the time that the ball passes 10 meters above the person's hand? So we threw it from here. This initial position, we call it 0. And we want to know how long it takes to reach this position here, which is plus 10 meters above the initial. Alright, so how are we going to solve that? Let's use the equation for position, right? So we have 10 equals to y naught is 0, v naught is plus 20 t, and g is minus 10 divided by 2 minus 5 t squared. So this is the equation that we need to solve to answer question E. If you solve this equation, you're going to get 2 answers. Now this is a quadratic equation, you get 2 answers, which are written here. You can solve in your calculator to get the value of that square root. What does it mean to have 2 answers? 2 times, and 2 times they are positive. Okay, so 2 meaningful results. What does it mean? Well, we have 2 times because the ball goes up and reaches this point 10. Keeps going up, reaches its highest position, then it comes down, and when it comes down, again it passes through the same position. So there are 2 instances where it passes through that 10 meters. So that we have 2 answers here, 2 valid answers. All right? Okay, so this is it. We can try to solve now one more problem. And this problem is from the book. But let's try to solve this problem in the next video, otherwise this video will be too long.